All right, welcome to another episode of Category Theory. This is session 12. We're going to be going over exercises, chapter 2. That is section 2.8. So the reading was to do some exercises and then present your solution. So I'm assuming nobody did all 18 exercises. No. So what I'm going to do is share my desktop. Okay. All right, so just going through some of these exercises, like 283 says, prove that inverses are unique. And that's actually something that we went over like in the first session or something. Or like the first couple of sessions. So I already have like notes on that from a previous session that inverses are unique. And so yeah, it's a pretty straightforward proof. You just appeal. So G and G prime are equal because G is G composed with id, and if F and G prime are inverses of each other, then F and G prime composed are the identity, and then we use the associative law to go to G composed F, and those are supposed to be inverses as well, and so that's equal to id, and then id composed G prime is G prime, and so we've proved that inverses are unique. And I'm also given that sort of as a program rather than a proof, because we know that programs and proofs are isomorphic.
So I had more of a chapter 2 answer to that question.
Yeah.
Which was if F has an inverse, if F has an inverse and it's an iso, right? And so and we know that every iso is monic, and so then if you have Fg, that's equal to ID on B, which is also equal to F on G prime, and we know that F is mono, and so therefore G is equal to G prime.
Wait, tell me that again. I just want to capture that.
Yeah. So if your arrow like F has an inverse G and G prime.
Okay.
Right.
So if Fg equals id,
yeah,
and Fg prime equals id.
Oh, I guess this isn't strictly an iso if we don't know the other direction. So maybe this is a bad proof actually.
Oh yeah. Well,
maybe it still holds though.
It might still hold. What is your
so the rest of my proof went F has an inverse, so it is an iso, and that is not true. But from there, every iso is an epi and a mono. And so then if we have Fg is equal to Fg prime is equal to ID on B, then we know that F is mono, then we can cancel the F's on the left, and then it gives us G is equal to G prime.
Wait, slower.
So exactly here, right? We know that both of these things are equal to ID.
Yes.
And if F is mono, then we can just cancel F out, right?
Yeah.
And so
if F is a mono,
then G is equal to G prime.
G is equal to G prime.
Yeah. But I got F is a mono because I said F is an iso, which is not true. So.
Yeah, it is. We're assuming F has an inverse.
Yeah.
So F is an iso. So it's both epic and monic.
Yes, that's what I was saying. I don't think this is true though, because you need an inverse on both sides to be iso, right? And we can only claim we have one of those inverses.
Well, so the assumption, I mean, the whole premise of the question is that F has an inverse, so that it is an iso.
Okay. Well, I'm happy with that then.
So we're saying the inverses of F are unique, right? So we know that F has an inverse, and if it has more than one, then they are the same one.
Yeah.
That's a really good argument. Yeah. So assuming F is an inverse, then F is an iso, so it's both epic and monic. And so if we have these two things and F is monic, then, well, obviously we can remove it. Awesome. That's a really good argument. much better than mine is sort of step by step. So then exercise 2.8.12, which is also, so these are the ones I'm kind of listing here are ones for which the answer is not given in the book. So the ones where the answer is given in the book, I feel that the answers are pretty good, and we can just kind of study those on our own, unless there are some that you want to go over specifically. But yeah, so exercise 2.8.12 says like prove that, what does it say? It says, show that any Boolean algebra B, Boolean homomorphisms from B to 2 correspond exactly to the ultrafilters in B. And we actually already did that. And that was session, oh, it was like a couple of sessions ago. We talked about ultrafilters. I think it's probably like session 8 or 9, probably 9. No, it was 8 because category session 7 is where we talked about Boolean algebras. All right, so we actually have a video of that one. So if people want to refer back to ultrafilters, there's a video on session 8, where we talked about how homomorphisms from the Boolean algebra to or into the Boolean algebra 2 are exactly the ultrafilters. Great. Also talks about what ultrafilters are. See, this is one of the benefits of like not taking Awodi at his word. Just like go check it, then you've already solved all of his exercises. Because basically, at the end of the chapter, he'll say like, now that I've said all of this stuff, don't take me at my word, and go solve it. Okay. So then I did exercise 2.8.15, and right. So this is the problem. This is the verbatim exercise. Given a category C with objects A and B, define the category C sub AB to have objects X, X1, X2, so these triplets, where X1 goes from X to A and X2 goes from X to B. And then it has arrows between these triplets, X with X1, X2, and Y with Y1, Y2, where there are arrows in the underlying category C from X to Y, such that these things hold that Y1 compose F is X1 and Y2 compose F is X2. And then we have to show that C sub AB has a terminal object just in case A and B have a product in C. Right, so it's easy to reason through this with diagrams. So we just take these triplets. So X1, X2 are triples like this, like at the top of this diagram. So there's some object in C, and there are arrows into A and B, respectively, called X1 and X2. And this line 20 here is an object in the category C sub AB. And then an arrow from this triplet at the top and this triple at the bottom is a diagram like this. So this whole diagram is an arrow in C sub AB, and it's uniquely determined by this function, or this arrow F in the underlying category C, which goes from X to Y. But so an arrow then in C sub AB is is such a function that makes this diagram commute. Okay. Yeah. So and then composition on these arrows, we just stick another arrow at the bottom. So if we have another object Z and then Z1 and Z2, they go both into A and B. Then we have some arrow G at the bottom here that makes the further diagram commute. So then if we think about that as a whole category, compositions on these sort of triples, and then we think about what is a terminal object in that category. Well, it's going to be some diagram, a triple like this, which has an arrow into it for every other such diagram. And so that's saying that given any x with arrows f and g into a and b respectively, there's going to be a unique homomorphism or a unique arrow from x to p, which makes the product triangle commute. That is, it's going to like the commutative diagram for the terminal object in this C sub AB category is exactly identical to the product diagram in C. So definitions of product in C and terminal object in C sub AB exactly coincide. So then C sub AB has a terminal object exactly when A and B have a product in C. I think we went over this sort of already, but I'm abusing ASCII a little bit here with this notation. So I'm just saying like this whole side of the page is A and this whole side of the page is B. And then these arrows go into A and B. Okay. So 2618 is next. That was a pretty simple one. So he gives the category type of types C lambda of the lambda calculus. Determine the product functor that goes from A comma B to the product of A and B explicitly. And then show that for any fixed type A, there's a functor from or there's a functor like this from C lambda to C lambda, which goes from some type X to the type A to X, to the type of arrows from A to X. Right, so it takes any type X to the type A to X. So the product functor is just the functor from the product category C lambda and C lambda to C lambda. And it just takes the pair of arrows FG in the product category to the single arrow, which is lambda of P, which is the product. And then it applies F to the first half of the product and G to the second half of the product and puts them together in a product, right? And then the functor taking any type X to the type A to X is just the reader monad or the reader functor. So we can just say, well, A arrow is a functor. So given any other type X, it's a functor such that F map is function composition. Pretty straightforward.
So I had a little difficulty just representing that first part in Haskell because functors only have one thing in Haskell, right?
Yeah.
So I made mine a bifunctor, which I think is fine, but
I think that's basically the same thing.
To like what we're saying, right?
Yeah.
Cool. Great.
Yeah. So it's a bifunctor. I think the important thing is that the mapping on the arrows. So taking the pair of arrows FG to a single arrow in lambda.
Right.
So then, yeah, you take the pair of arrows that operate on the elements of the product to one arrow that operates on both sides of the product.
Yeah. Cool.
Yeah. Thanks. And then there was exercise 2818. Sandy, do you have a screen to share?
I do.
With regard to that?
I do. Share screen. I can't do it while you're sharing.
Oh, do I have to stop?
Apparently.
Okay. Stop share.
Starting share. Share this. Cool. And maybe you can see my screen now?
We can.
Great. So at the bottom here, 2818. I want to show that there's some forgetful functor from monoic sets. I don't know how right this is, but I came up with the right representation apparently, so that's a good sign. And so I was kind of like, what is a representable functor? And we want some like natural isomorphism between the Hom set of the reader, or I guess the reader, and some object A and C. So what I did is I built this kind of representable machinery where I've got like some type, which is my representation, and then these are natural transformations, like from my functor X to this reader, like Hom set. So if I can go both ways, then I have something representable. So I made this like silly forgetful thing, which is like, if I have some monoid M, then I can get forgetful and like there isn't a monoid instance, and so I've forgotten my monoid instance.
Yeah. So that's just the type M, right? Yeah. But
yeah,
that's a good way of representing it.
And so this thing isn't a Haskell functor, but that's okay. So now kind of I'm just winging it, and so I need some like object A in monoid, right? And so like the only distinguished thing I can think of is like a free monoid. Like I can't imagine there'd be any other mapping that would make any sort of sense. So that's like over some A, but I need some set A. And I'm like, I don't know. What kind of distinguished sets do we have? We have like void, but there's not going to be an interesting monoid over that. And so the other thing I could think of was like, I guess we also have a singleton set, right? And so that's a unit in Haskell. So I've got this thing here, right? And so a list of unit is isomorphic to nat, and so I'm like, okay, we'll use nat instead. So kind of powering through all this stuff. If I have 0, then like the only thing that could possibly is empty. And then kind of I'm making things up as I go here. And so really the only other reasonable thing I can think of is like, if we have n, then that's kind of the same as like replicating this m that I have n times and squishing them together. Like those are the only things I can do with a monoid. I realize actually this could be simplified into one step. I don't need a special case for 0, but that's what I have. Apparently this is right, but I think it might be right for the wrong reasons. So I'm really interested to see what you have for now.
Yeah, that looks totally right. I don't think it's right for the wrong reasons.
I'm going to stop sharing and maybe you see yours as well.
Oh yeah, I will share again. All right, come on. Zoom wants to be full screen for some reason. Okay. Here's my solution. But yeah, I thought this actually was pretty tough to puzzle through. But yeah, the forgetful functor U from Monteset is representable. So it has to be isomorphic, like you said, from it has to be isomorphic to this functor from set to set. That is, it goes from the Hom set of monoid homomorphisms from M to A to the set A, right?
Should that functor be from monoid to set? Because the underline would be some monoid, right?
Oh, you mean this Hom functor here?
Yeah. Yeah.
No. So,
the Hom functor is in set, right? But it's an object in set.
Yeah. So this is an object in set.
Yes.
It's the set of homomorphisms. It's a set of monoid homomorphisms from M, right?
Yes.
Even though M is an object in Mon, the set of arrows out of Mon is in set.
Yeah. Okay.
Right. So this is an endofunctor in set. But we're going to say that it's representable. This U is representable because it's isomorphic to this functor, endofunctor in set. So this functor is basically that. So given a monoid M, it's M to whatever, right? So in Hask, it's this functor here. Right, so then we just have to find a natural isomorphism from U to this Hom thing here. So a reminder on what a natural transformation is it has to make this diagram commute. So we have to find some eta, which has an inverse. That is, it's an iso. So we have to find some eta that goes from the underlying set of A into some monoid homomorphism from M to A, such that if we have some other monoid homomorphism F and we compose that one with the homomorphism we found, we should get some homomorphism B, such that if we go F and then eta, we get to the same place, right? So F of eta of A and M should be the same as eta of F of A and M for any monoid homomorphisms F and any elements M of the monoid M and any element A of the set. Of the monoid A. So this has to work just for some monoid M. It doesn't have to work for all monoids. So our task is really to find the monoid M that makes this work. So we need these two things. We need like eta, which goes from A to these monoid homomorphisms from M to A. And we need epsilon, which is the inverse of eta, which goes from these monoid homomorphisms from M to A into the monoid A. Right, so yeah, so M to A has to be a monoid homomorphism and it must preserve empties and appends. Eta and epsilon have to be inverses of one another. So we know that there's a monoid with the homomorphisms into every other. So that's the free monoid. We know that we can definitely get that one. So we could pick M to be list of A, right? So we could, for instance, say like, well, given an A and a list of A, we can get an A, right? I mean, that's true. And then given a function from a list of A to an A, we can get an A. That's also true. But like, can we construct an isomorphism there? And the answer to that is no. Because if you think about epsilon, like how would you implement epsilon? Like what would you pass as the argument to this function? If you had like a list of A, right? I mean, if M was a list of A, how would you construct the list of A? Well, it would have to be either list of mempty or, some arbitrary long list of mempties, or it would have to be the empty list. And so there's really no way to make that an inverse of eta, because here you'd have to do something like, this is a list full of A's, and then I have an A here. Well, I could return any of the A's in here, or I could return this A, or any kind of sum of these A's, right? So list of A is in a sense too big to be a solution for this. However, we can pick like the smallest thing that could possibly work, which is unit. So then M, we set that to list of unit, which is, like Sandy said, it's isomorphic to the natural numbers. So empty list is 0. The list of one unit is 1. List of 2 units is 2, etc. So then we can implement those in Haskell like this. So eta is fold map with const of A. Right, so we map over the list, assigning every unit in the list to the A that was given, and then we fold all the A's together to get a single A. Right, so it's that given A n times, where n is this natural number here. And then the inverse of that is epsilon, which, given one of these monoid homomorphisms from natural numbers to A, will then give us an A. And what we pass to that monoid homomorphism is the number 1. if you think about this sort of intuitively, like why one, you think about that these have to be monoid homomorphisms. So you already know that any monoid homomorphism maps zeros. That is, it maps Mempties. And you know that it will map like n plus m, right? It'll map that to the corresponding sort of sum. So really, the only thing that you need to be able to sort of prove is that you can map the element 1 into your monoid A somehow. So basically, you just say that, well, given my A, I'm just going to say that 1 is mapped to that A. So 1 maps to every A using eta. And then epsilon says the inverse, which is that every homomorphism like this maps 1 to some A, right? And so we're just going to like ask what that is, right? Ask what that A is. And yeah, also intuitively, then you can see that these sort of have the same size, right? So there's some number of A's, and that number is a natural number, right? There's 0 or more A's for sure.
That's really interesting, actually. I didn't think about that.
Yeah, and there are if A is a monoid, really, then there are A natural numbers as well. Or is that true? No, it's not. But yeah, there are n ways of constructing an A. Right. So then let's prove it. So the epsilon composed with eta being the identity is the easy case. So epsilon of eta of A is the same as, so we substitute in the definition of eta. So it's, no, sorry, we substitute in the definition of epsilon. So epsilon of eta of A is just eta of A of 1. And then we say, well, eta is fold map composed with const. So fold map const of A of 1. And so if we, const of A is the function that always returns A. If we map that over the 1 element list, that's going to be the list that contains just A. And if we fold map that, well, that's going to be A plus 0. I mean, A plus Menti, right? It's just A. And so that's proved. I guess I should say A equals A down here. The other case is where we have eta of epsilon of f of x's equals f of x's. That is, eta composed with epsilon is the identity. So then we substitute in the definition of eta, which is fold map const. Substitute in then, simplify that. So it's fold map of const of epsilon of f. So then this is a function that maps over a list and puts epsilon of f into every element of that list. So it replaces the units in the list with epsilon of f. Actually, I have a type error here. There should be x's in here. I can just remove the x's everywhere. Right? Okay. And then what we have to do is show that this holds. That like folding a list with f applied to 1, like folding a list full of f applied to 1 is the same as just applying f. And it turns out that that is we have to appeal to the monoid homomorphism law. Like there are really only 2 things that the list x's on the n tier could be. it could be either the empty list or it could be a composite list. So if it's the empty list, then that's really simple because fold map of the empty list is mempty, and f of the empty list has to be mempty as well because f is a monoid homomorphism. So mempty equals mempty. That case is now proved. In the other case, we know we have a composite list. And I'm going to say, since composition is associative, I'm just going to pull out one of those units into its own list at the front. So it's 1 plus some other number, b, right? So if we think about this natural numbers, this is, const f of 1, and this list here is really the natural number 1 plus n. And I'm going to say that this whole expression here is equal to, actually, why don't we do, no, that didn't work. Oh, yeah, that's great. That's much better. It's easier to read this way. Right, so right. So since it's we're folding this list, we're summing 1 plus b. But no, actually, it makes it harder to read. Sorry about that. Let's go back. Okay, great. Right. Okay, so I've pulled out one on either side here out of this list, and b is the rest of the list. Then that is going to be the same by the homomorphism law. That's really going to be the same as, folding this list, which just has 1, and then should be mapend, and then mapending, fold map of the other thing, right? That should be mapend as well. So fold map of a composite list should be the same as composing the folds of the components. So I just want to fold the 1 and mapend the fold of the rest, and that should be the same. Okay? Mapend. Why do I have this twice? Don't know. Anyway, so folding const of f of unit over the single element lists, well, that's just, f of 1, right? So it's going to be whatever this const thing is. So fold map const of a over the single element list is just f of a. And then that's going to be, that's composed, m appended with the rest of the fold of the rest of the list. And that should be the same as f of this composite list. Now, invoking the monoid homomorphism law on the other side, now we can say that, well, f of this composite list should be the same as f of the single element m append f of the rest of the list. And so now we have these expressions on both sides that look very similar. And so f of something, m append some other thing, is the same as f of something, m append this other thing. So therefore, we know that these two sides are the same, f of 1. So all we'd have to say is that we have to pull out the rest of this stuff and say that, well, fold map const f of b is the same as f of b. And that's the proposition we started with. And so we appeal to induction and say that we can keep doing this until we get to the empty list, until b is empty. And we're done, right? So it just proceeds by induction on the natural numbers. And we have to appeal to the homomorphism law. So the functor is the functor, the forgetful functor from monoids to sets is represented by the initial object in monoids, which is the free monoid on one generator, which is the natural numbers with addition. U. Sorry, that was a bit long-winded, but that's the answer.
Sweet. Homomorphisms are crazy. Wild.
Sorry, what?
Homomorphisms are wild. I'm glad, thanks for going through the proof of that. I want to study that slowly.
Yeah, man.
In lots of time.
Yeah, homomorphisms are everything. Like monoid homomorphisms, and then functors are category homomorphisms. Monoid homomorphisms are functors because monoids are single object categories. But I think what Wody wants us to see here, or sort of get a feel for, is the Yoneda lemma. So this is really Yoneda's lemma in disguise, or under the hood working here. Because if we look at this thing here. So Yoneda's lemma says that that there's a natural isomorphism between, functors like this and functors from like hom of something to f, right? So if we study Yoneda's lemma, then we'll see that looks very similar. In fact, I think if we go to representable functors on representable functor, you can see that I've been studying this.
I've got a lot of similar searches trying to answer that last question.
Yeah, so if we just look at representable functor on Wikipedia, there's a reference to Yoneda's lemma. So it says that natural transformations from hom of A, with this whole. So natural transformations from this hom set functor to F are in one-to-one correspondence with the elements of F of A. So that's in play here. And we'll work up to that and eventually get to Yoneda's lemma at some later time. All right, so next time we're going to start with chapter 3 on duality. So we're going to flip all of our arrows. We're going to start talking about coproducts. So we should read 3.1 and 3.2. So I think 3.1 is not really enough. There's not a lot of content there. So let's look at 3.1 and 3.2 on coproducts. That's actually quite a lot. Where does 3.3 start? Is it? Oh, equalizers. Yeah, so 61. So pages 53 to 61.
Sounds good.
All right. I'll see you next week.
Cool. Yeah.
Thank you.